this lesson, we want to look at some questions, and the first question we're going to look at is, does the sine of angle A plus angle B equal the sine of angle A plus the sine of angle B? In other words, can we distribute the sine to the sum of these two angles? Well, let's take some angles that we know, and so let's look at the sine of 30 plus 60 degrees. And let's see, does that equal the sine of 30 plus the sine of 60? Well, we know that 30 plus 60 is 90. So this is the same as the sine of 90 degrees, and we know that the sine of 90 degrees is 1. Well, if we go over here, the sine of 30 we've learned to be 1/2, and the sine of 60 is the square root of 3 over 2. So this equals 1 plus the square root of 3 over 2. And we can see that those two things are not equal. Square root of 3 is more than 1, and so our numerator is more than 2, and so this value is more than 1. But they're not equal. So what we're going to find is we cannot distribute. We've said many times before that a function, sine, cosine, tangent, by itself has no meaning. You always have to have it with an angle. And so we can't distribute then sine because it's not a function in itself. So we've got some identities that we can deal with, and I'm not going to go through and show you how we derive these identities, but these are called our sum and difference identities or formulas. And so we have the sine of A plus B, angle A plus B. And most of your trig books have where these are proved, and so if you want to see how they're derived, you can look there, but I'm not going to take the time. It's a little lengthy. But the sine of the sum of two angles is equal to, and I'm going to call this the first angle and this the second, and I always say it with the first and second. It's the sine of the first, cosine of the second, minus cosine of the first, sine of the second. I knew I was saying that wrong. That's a plus. The sine of A plus B, it's the sine of the first, cosine of the second, plus cosine of the first, sine of the second. The sine of A minus B, the difference of two angles, is the sine of the first, cosine of the second, minus cosine of the first, sine of the second. Now, we also have formulas for the cosine, for the sum and difference, and the tangent. I'm going to go ahead and put those. The cosine of the sum of two angles, A plus B, is the cosine of the first, cosine of the second, minus sine of the first, sine of the second. And if we look at the difference of two angles, then the cosine of A minus B is equal to the cosine of the first, cosine of the second, plus sine of the first, sine of the second. So you can see they're very similar. For cosine, when you're adding the two angles, then it's a subtraction. When you subtract the two angles, it's a plus. For sine, they have the same sign. And then let's look at tangent. The tangent of the sum of two angles. It's the tangent of the first plus the tangent of the second divided by 1 minus tangent of the first times the tangent of the second. And the tangent of A minus B. It's the tangent of the first minus the tangent of the second over 1 plus tangent of the first, tangent of the second. So whatever sign you have between those is what we have in the numerator, and we have the opposite sign in the denominator. So these are what we call our sum and difference identities. And anytime you're trying to find the function for the sum of two angles or the difference of two angles, then you would use these. If you had two angles drawn adjacent to each other, then, and you were wanting to find the sum of, or the difference of those two angles, then you would use these. Now, one of our big uses for our sum and difference angles is to get some exact values for angles that we couldn't on our own. So let's look at how we could use these to find exact values for some specific angles. Let's start with the sine of 105. Now, we don't know exactly what 105 is, but if we can write 105 as the sum or difference of angles we do know. Now the angles we do know, 30, 45, 60, 90, 135, 120, 135, 150, 180, and we can keep going. Those angles whose reference angle is 30, 45, or 60. So if we can write these as the sum or difference of two of those angles, then we're going to be able to find exact values. Now, to know if you can, we always have to use 45. The reason, if we add 30 and 60, which are two angles we know, we get 90. Well, we already know 90. If we add 30 plus 120, two angles that we know. Well, we already know that. It's 150, whose reference angle is 30. So these are ones we already know. So the one that we're going to use, it will always be 45. So if you're trying to figure out what angles to use, then take your angle and either add or subtract 45. Now if we subtract 45, we get 60. So we can write 105 as 60 plus 45. If we added 45, we would get 150. So we could write 105 as 150 minus 45. Now I always recommend that you stay in the first quadrant if you can. Sometimes we can't, but in this case we can. So this is the same as the sine of 45 plus 60. Now, if we use our formula, this is the sine of the first, cosine of the second, plus cosine of the first, sine of the second. And we know these values. So the sine of 45, we've learned to be the square root of 2 over 2. We're in the first quadrant, so it's positive. The cosine of 60 is 1/2, where it's in the first quadrant, so we're positive. The cosine of 45 is square root of 2 over 2, first quadrant, positive. Sine of 60, square root of 3 over 2, first quadrant, positive. So what we ended up with is the square root of 2 over 4 plus the square root of 6 over 4, which we would write as the square root of 2 plus the square root of 6 over 4. And that gives us an exact value for the sine of 105. Now let me just go through here and do this again, but use that 150 minus 45 that we talked about, just to show you why that it will work, but also why I like to keep it in the first quadrant. This would be the sine of the first, cosine of the second, minus cosine of the first, sine of the second. Okay, 150. For 150, our reference angle is 30 degrees. So we work it out. The sine of 30 degrees is 1/2, but we're in the second quadrant, so the sine is positive. The cosine of 45, square root of 2 over 2, we're in the first quadrant, positive. The cosine of 30 is the square root of 3 over 2, but we were in the second quadrant, so that's negative. And the sine of 45, square root of 2 over 2. So you can see we get the square root of 2 over 4, and a negative times a negative times a positive is a positive, square root of 6 over 4. So we got the same answer, but we had to remember here that we were in the second quadrant, and in the second quadrant cosine is negative. So if you can stick with the first quadrant, then you know that they're all going to be positive. But you can do them in other quadrants. You just have to be careful. Okay, let's look at another one. Say we want the cosine of 75 degrees. Well, again, we can add or subtract 45. So if we subtract 45, we get 30. So 75 is 30 plus 45. So this is the cosine of 30 plus 45. Now we could have added 45 to that and we would have gotten 120. So 120 minus 45. So we would still get that. We can still get it by subtracting. So this would be the cosine of the first, cosine of the second, minus sine of the first, sine of the second. Okay, the cosine of 30 is the square root of 3 over 2. Cosine of 45 is the square root of 2 over 2. Sine of 30 is 1/2. And the sine of 45 square root of 2 over 2. So we end up with the square root of 6 minus the square root of 2 all over 4. And we like to write it in this form. And this is an exact value. And so this gives us, this helps us then as we go through to find our exact values for angles. And the more the things that you can keep exact, the better. And if you wanted to check your answer, you can pull up our calculator and we can find the cosine. Let's make sure it's in the degree mode. So we could find the cosine of 75 degrees. Okay, we can also take parentheses the square root of 6 minus the square root of 2, close the numerator, divided by 4, and we don't get the same answer. So I need to figure out what I've done incorrectly. Okay, my work's correct. Let me go back and check. Okay, I thought I put it in the degree mode, but it appears that I didn't. So let me go back now and do the cosine of 75. Yes. So a while ago when I thought I put it in the degree mode, I didn't. And so it didn't give me the correct answer. I wasn't in degrees. So we have our sum and difference of our angles. Let's do another one. And let's do one with radians. Let's do one, the cosine of pi over 12. Now you might say, well, I don't know how to figure out what my angles to use. Again, we're going to add or subtract 45. And if you remember, in radians, 45 was pi over 4. And so we can come through and we can take pi over 12. And in this case, I would add pi over 4 because if we subtract it, we're going to end up with a negative angle. So we get a common denominator, which is 12. So this would be 3 pi over 4 over 12. Multiplying both the numerator and denominator by 3, which gives us 4 pi over 12, and that reduces to pi over 3. And we know pi over 3. So this is the same as, okay, you can see it's going to be the 4/12 minus the 3/12. Well, 4/12 is pi over 3 minus 3/12, which is pi over 4, would be the pi over 12. So we can expand it. It's the cosine of the first, cosine of the second, plus sine of the first, sine of the second. And once we have it written as a sum or difference, we work this exactly the same. I just wanted to show you how if you were given your angle in radians, it's still not hard. You take whatever that angle is and you add or subtract pi over 4. If the angle's bigger than pi over 4, you can subtract it. If it's smaller, you can add it. So now we can go through and work this out. We know that this reference angle is 60, and the denominator's 3, the reference angle is 60, so the cosine of 60 is 1/2. The reference angle, here's 45. Cosine of 45, square root of 2 over 2. The sine of 60 is square root of 3 over 2. And the sine of 45 is square root of 2 over 2. And so we end up with the square root of 2 plus the square root of 6 over 4. Now you may have noticed that we keep getting the same types of answers. They have the same numbers, square root of 6 minus the square root of 2 over 4, square root of 2 over 4 plus the square root of 6 over 4. So this will always be true because we're going to be using the same angles. We're using the angles that we know, which are 30, 45, and 60, are angles that have those as their reference angles. So that's going to always happen. Let's take a tangent. Let's say we want the tangent of 165 degrees. Now we need to figure out what two angles to use. So 165 minus 45 would be 120. So this is the same as the tangent of 120 plus 45. And it doesn't matter, you can put 45 plus 120. So our identity tells us that that's the tangent of the first plus the tangent of the second divided by 1 minus the tangent of the first times the tangent of the second. Well, for tangent, remember here our reference angle is 60. When you've got to rotate it around 120 degrees, your reference angle is 60. The tangent of 60 is square root of 3. But we're in the second quadrant, so it will be negative. The tangent of 45 is 1 over 1 minus negative square root of 3 times 1. So I'm going to switch these around and call this 1 minus the square root of 3 and this would be 1 plus the square root of 3, a negative times a negative. Now, some books will let you leave it in that form. Others will tell you that you need to rationalize. If we were going to rationalize this, we'd multiply by the conjugate, which is 1 minus the square root of 3. And so what we would get in our numerator, multiplying those out, we have 1 minus the square root of 3 minus the square root of 3 plus 3. In our denominator, these are conjugates, so it's the first term squared minus the last term squared. And then combining our like terms, we have 4 minus 2 square roots of 3 over negative 2. So 4 divided by negative 2 is negative 2. Negative 2 divided by negative 2 is a positive. And we get negative 2 plus the square root of 3. Now, there are some things that can happen with tangent that sometimes make it just a little bit harder. Let me show you. Let's take this same one, and let's take the 165 and add 45 to it. And we would have gotten 210. So let's take this and do this as 210 minus 45. Now we're going to get the same answer. The tangent of 210 minus 45. Okay, that's the tangent of the first minus the tangent of the second over 1 plus the tangent of the first, tangent of the second. Now for 210, our reference angle is 30, and we're in the third quadrant. So the tangent of 30 is square root of 3 over 3. We're in the third quadrant, so it's positive, minus tangent of 45 is 1 over 1 plus the square root of 3 over 3 times 1. So what we have is a complex fraction. We have a fraction over a fraction. Now, what we can do is we can get us a common denominator for both our numerator and denominator. And if we do that, we've got the square root of 3 over 3 minus 1 would be 3/3. In the denominator, it would be 3/3 plus the square root of 3 over 3, which gives us the square root of 3 minus 3 over 3 plus the square root of 3. Remember, once you get that common denominator, then your denominators cancel and you have this numerator over this numerator. Now we're going to have to turn around and rationalize. So we'll multiply by 3 minus the square root of 3. So multiplying that out, we have 3 square roots of 3 minus 3 minus 9 plus 3 square roots of 3. For the denominator, these are conjugates, so it's the first term minus the last term, which would be 3. So combining our like terms, we end up with 6 square roots of 3 minus 12 over 6. And we can divide, so we end up with the square root of 3 minus 2. And if we go back to the other one that we had negative 2 plus the square root of 3. So you can see we got the same answers, but this one was just a little bit easier. When you can, it's easier to have an angle whose reference angle is 60 when you're dealing with tangent because you don't have the fraction. You just have the square root of 3. If your reference angle is 30, then you're going to have to deal with the fraction of square root of 3 over 3. So that's just something that you might look at when you're working with your tangent, is you may want to, look at adding or subtracting and then use the one that would give you a reference angle of 60. But it wasn't that hard to deal with the square root of 3 over 3. You simply got you a common denominator for your numerator and denominator. Then they canceled, and that left you with your fraction that was this numerator over this numerator. Then you had to rationalize. So this is how we can find some other exact values using our sum and difference formulas. Now there's other things that we like to do with our sum and difference formulas, and sometimes we can use them to simplify some different expressions. So let's look at this one. Say that we were given the cosine of 3x cosine times the cosine of 2x plus the sine of 3x times the sine of 2x. Now, if we can, we'd like to write this as a single function. And we've got some things that could be very complicated, but notice that our angles, this angle and this angle, our first angles are the same, and our second angles are the same. It's cosine, cosine. So if we go back and we look, cosine of the first, cosine of the second, sine of the first, sine of the second. So it looks like we could use our cosine of 3x. Now remember, it's always the opposite for cosine minus 2x. If we expanded this, it's the cosine of the first, cosine of the second, plus sine of the first, sine of the second. And now we can combine those. 3x minus 2x is x. So we've taken something that looked very complicated, and we were able to write it down as a single function. So it's just a matter of looking at them and finding out which function they resemble so that you can go about and you can write them then as a single function. If we looked at one more, let's say we have the sine of 15 times the cosine of 75 plus the cosine of 15 sine of 75. Now again, it's the sine of the first, cosine of the second, plus cosine of the first, sine of the second. This was our sine function. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. So we can write this then as the sine of 15 plus 75, which is the sine of 90, and we know that the sine of 90 is 1. So we've simplified that down to where we had the answer. And so this gives us, by looking back and at our functions, then we can take some things that are a little bit more complicated, and by finding a function that it's similar to, we can write it as a single function and possibly even come up with the answer to that. Okay. Now, There are also times when we've been given our functions and our functions of angles. We don't know what the angles are, but we know what some of the functions are. And we're going to be able to use these identities to come up with the sum or the difference. Let's say that we were told that the sine of angle A was 3/5 and that A is in quadrant 2. Now it's going to be important for us to know what quadrant it's in. And the sine of angle B is -5/13 and B is in quadrant 3. Now we want to find the sine of angle A plus B. So whatever these angles are, we were wanting to add them together. Now, we don't know what the angles are and that it doesn't matter. We're still going to be able to use our functions. So let's expand it. This is the sine of the first, cosine of the second, plus cosine of the first, sine of the second. Now we know the sine of A, it's 3/5. But we don't know the cosine of B. So what we're going to do is some things that we did a lot earlier. We know the angle. We're going to draw us a triangle. And if this is angle B, then the sine is the opposite over the hypotenuse. And if we use the Pythagorean theorem, we've got us a 5, 12, 13. Most of the time, these are going to be your special triangles. And we're in quadrant 3. So the cosine of B is the adjacent over the hypotenuse. We're in quadrant 3, so cosine is negative. That's going to be important. You have to deal with your quadrant. Now, cosine of A, we don't know that. So again, we're going to draw our triangles. And we know that the sine is the opposite over the hypotenuse. Using our Pythagorean theorem, this is a 3, 4, 5. And we're in quadrant 2. So the cosine of A is 4/5. We're in quadrant 2, so the cosine is negative. And the sine of B is -5/13. Now we can do our multiplying. We have -36/65. We have a positive times a negative times a negative, which makes that positive 20/65, which would be -16/65. So now we were able to find the sine of the sum of those two angles and without having to find the angles. But it is important that you keep track of the quadrant that you're in. Okay. And if we had needed to find also the sine of A minus B, the only difference in that is that's a minus here. So that means that at this stage, it would have been a -36/65. And then we would have had a negative times a negative times a negative. So that would have been a -20/65. So it's not that you have to do the whole problem again. It's just that one sign is going to change. So it would be -56/65. Okay, if we took okay, let's say that well, let's go back. There's one other question I want to ask in this last one. And that's, what quadrant are we in? We've got -16/65, And we want to know, well, what quadrant is that in? Because we haven't looked at that. Well, to look at it on our own, let's just take the sign of a plus b. It turned out to be negative. So we know the sign's negative in the third or fourth quadrant. So to be able to know which quadrant the sum of them end up being in, let's go through and let's take the cosine of a plus b. Well, that's the cosine of the first, cosine of the second, minus sine of the first, sine of the second. Well, the cosine of a, now we're using those same little triangles. So the cosine of a is 4/5. We're in quadrant 2, so it's negative. The cosine of b would be 12/13. We're in quadrant 3, so it was negative. The sine of a would be 3/5. We're in quadrant 2, so it was positive. And the sine of b would be 5/13. We're in quadrant 3, so it's negative. So we end up with 48/65. We have a negative times a negative, so that's a positive 15/65, which gives us a total of 63/65. Now what we notice up here is that the sign of a plus b was negative, is negative 16/65. The cosine of a plus b is positive. So this means we've got to have ended up in quadrant 4, because that's the quadrant where the sine is negative and the cosine is positive. So it actually takes two functions, are doing two different functions to be able to know then which quadrant we're in. But that's an easy way of knowing, is by looking at your signs. Let's take one more of these and look at it. Uh, okay, let's take this difference, the sine of a minus b. We want to find out what that is when the cosine of a is negative 15/17 and a is in quadrant 3, and the tangent of b is negative 12/5 and b is in quadrant 4. Well, if we expand this, it's the sine of the first, cosine of the second, minus cosine of the first, sine of the second. Now, we have to draw our triangles to be able to find these. So let's just go ahead and draw them. Probably should have done that while I had a little bit more room. But if this is angle A, the cosine is 15/17. And if you remember, we have an 8/15/17 Pythagorean triple, and we're in quadrant 3. B, drawing our triangle for it, the tangent's 12/5. Well, this is a 5, 12, 13, and we're in quadrant 4. So the sine of A is 8/17. We're in quadrant 3, so it's negative. The cosine of b is 5/13. We're in quadrant 4, so it's positive. The cosine of a is 15/17. We're in quadrant 3, so it's negative. And the sine of b is 12/13. We're in quadrant 4, so it's negative. And then it's a matter of multiplying, so we end up with negative 40. And 17 times 13, you can use your calculators, 221. Now we have a negative times a negative times a negative, which will make this negative. 15 times 12 is 180 2/21. So we end up with negative 220 2/21. Okay, let's take this and let's find the tangent of a minus b. Well, that's the tangent of the first minus the tangent of the second over 1 plus tangent of the first, tangent of the second. Okay, the tangent of angle A is 8/15. We're in quadrant 3, so it's positive. The tangent of B is 12/5. We're in quadrant 4, so it's negative. Over 1 plus 8/15 times negative 12/5. Now, as we go through and do this, I want to make a recommendation. And when I deal with tangent, I always get my common denominator by multiplying those two together. Because down here you're going to be multiplying them. Now, sometimes we might be able to cancel and make the problem a little bit easier. But most of the time we can't. And so your denominator down here is going to be their product. So I just go ahead and make that my common denominator. So in my numerator, my common denominator is 5 times 15, so it would be 75. Then I need to multiply this by 5 to make it 75, so 8 times 5 is 40. A negative times a negative is a positive. And 5 times 15 would be 75. So 12 times 15 is 180. Then for my denominator, I want my common denominator to be 75. Now 1 would be 75/75. I have a positive times a positive times a negative, and this is 8 times 12 is 96 over 75. This was already over 75 because that was the product. So this was 96/75. My 1 I changed to 75/75. And the reason I did that is because now my denominators cancel and I end up with 220 over negative 21, which would be a negative 220/21. So again, if I wanted to decide what quadrant I was in, the sign was negative. The sign of the difference was negative, which means I was in the third or the fourth. My tangent was negative, so that's in the second or the fourth. So that means I'm in the fourth quadrant for A minus B. But it's just using our triangles and our formulas to expand them. And let's look at this one. Let's say that we were given that the secant of angle A was the square root of 5, and A is in quadrant 1, and the secant of B is the square root of 10, and we're in quadrant 1. And what we want to find is the secant of a plus b. Now, what we know is that the secant's the reciprocal of the cosine. So this is 1 over the cosine of a plus b. And we'll expand that. That's 1 over the cosine of the first, cosine of the second, minus sine of the first, sine of the second. And we will fill in. Now we need to draw our triangles. If this is angle A, okay, the secant's the reciprocal of the cosine, so this means this is square root of 5 over 1. And we need to find this other side. Well, we'll have to use our Pythagorean theorem of 1 squared plus, let's just call that x squared, equals the square root of 5 squared. So 1 plus x squared equals 5. Subtracting x squared equals 4. So x is 2. And we're in quadrant 1, so it was a positive. For b, okay, we're going to have the square root of 10 over 1. And if we go through, then we've got 1 squared, which is 1, plus y squared equals the square root of 10 squared. So 1 plus y squared equals 10. Y squared equals 9, so y equals 3. And we're in quadrant 1, so it was positive. So now we have 1 over the cosine of the a would be 1 over the square root of 5. So we have 1 over the square root of 5. We're in the first quadrant, so it's positive. The cosine of b is 1 over the square root of 10. First quadrant positive. The sine of a is 2 over the square root of 5. And the sine of b is 3 over the square root of 10. So we have 1 over, this is going to be 1 over square root of 50, or that's 5 square roots of 2, minus 6 over square root of 50, which is 5 square roots of 2. So we have 1 over negative 5 over 5 square roots of 2, or 1 over negative 1 over the square root of 2. Now, we're going to do our division, so we'll multiply by the reciprocal. So we have 1 times negative square root of 2, which is negative square root of 2. So no matter what you're given, you can draw your triangle and you can put it in. If you needed to work with one of your reciprocal functions, then you could find that. We could have just gone through and found the cosine of a plus b and then taken the reciprocal of that answer instead of having to deal with the 1 all the way through. We could have done this value, which we would have gotten then 1 over the square root of 2, and then taken the reciprocal of that. So we can find our other functions with this. Let's look at one last one along this line, and then we will look at a few identities. Let's say that we were given that the tangent of a plus b was 2 and the tangent of B was 1/3, we want to find the tangent of A. Well, we start out, how did we get the tangent of A plus B? Well, the tangent of A plus B was the tangent of the first plus the tangent of the second over 1 minus the tangent of A times the tangent of B. Now, if we go in and fill in what we know that the tangent of A plus B is 2. We know that we don't know the tangent of A. That's what we're trying to find. We know that the tangent of B is 1/3 over 1 minus the tangent of A times 1/3. Well, let's do a little simplifying here. This is 2 is equal to the tangent of A plus 1/3 over 1 minus 1/3 tangent A, or tangent A over 3. Now, this is a ratio, so we can do our cross product. We can treat this as 2 over 1, and we can do the cross product. 2 times this is equal to 1 times this. So we have 2 times 1 minus tangent A over 3 is equal to tangent A plus 1/3. So distributing, we have 2 minus 2 tangent A over 3 equals tangent A plus 1/3. Now, one of the things we learn in algebra is if we've got fractions and we don't want to have to deal with the fractions, we can multiply both sides of our equation by the common denominator, which in this case is 3. So if I go through and I multiply each term times 3, then I'm going to get 6 minus, my 3's will cancel, 2 tangent A equals 3 tangent A plus 1. And then I don't have to deal with the fractions. So now I want to get my tangent A's on the same side, so I would add 2 tangent A to both sides. That would give me 5 tangent A plus 1. Want to get it by itself, so I'll subtract 1. So 5 equals 5 tangent A. And then dividing both sides by 5, I get 1 equals tangent A. So given what the sum of those were and what one of the functions was, we could find the other one. So it's a nice little way to solve. Okay, and then we want to look at just some identities to prove. And these will be a little bit different than proving the identities that we have in the past. Because most of the time what it's going to be is a matter of expanding. Let's say we want to prove that the sine of pi over 6 plus x plus the sine of pi over 6 minus x equaled the cosine of x. Now, what we're going to do in these is we're just going to expand our formulas. This is the sine of the first, cosine of the second, plus cosine of the first, sine of the second. Then expanding this one, it's the sine of the first, cosine of the second, minus cosine of the first, sine of the second. Okay, and we want to show, I didn't draw my line because I knew I was going to need a lot of space, but we're wanting to show that this is the cosine of x. Well, if we look at some of the things that we have even before we start uh, combining, we have a plus cosine pi over 6 times sine x minus that. So those are going to subtract out. And so what we've ended up with is 2 sine pi over 6 cosine x. Well, let's work this out. Pi over 6, our reference angle is 30, and the sine of 30 is 1/2 cosine x, and 2 times 1/2 is 1. And so it was just a matter of expanding it and then uh, evaluating what our function was. So we can go through and do several of these, and it makes some nice proofs that are not as difficult as some in the past. You're not having to look at a lot of your uh, basic identities that you can substitute in. You're mainly just expanding this. So what we're looking at here is dealing with our sum and difference formulas and ways that we can use them to find exact values for other angles, angles that are sums and differences of 45, 30, 60, and then also given two functions, being able to find the sum or difference of the two angles, and then dealing with some identities.